Excellent. All right. All right, now we're recording.
Okay.
Well, welcome everybody. Thanks for being here for this month's World Above the Tetons Science Speaker Series. We've got a couple more events coming up in July and as well in August, and we'll get that updated on our website in the upcoming days. And so do check back on that to see what the upcoming events are. Just as a reminder, after our presentation this evening, we will have some door prizes with some fun stuff to give all of you who are in attendance today. And then we'll also do the raffle drawing for one of Mike Adler's astrophotography prints. And so stick around after the Q&A for those prizes. So tonight, it's my pleasure to introduce Kelly Lively, who's the Radioisotope Department Manager at Idaho National Laboratory. I've never been to Idaho National Labs, even though it's so close to us here in Jackson, but now I've got a really good excuse to get there soon.
Well, let's hope so, motivation then.
Yeah. Well, Kelly, thank you so much for joining us tonight, and I'll hand it over to you.
Thank you so much for the introduction, and it is absolutely my pleasure to speak to your group tonight. I was thrilled to have the opportunity to do that, and maybe you'll learn a little bit more about what we do out on the desert site at Idaho National Laboratory. So I am the department manager of Radioisotope Power Systems. I've been with the laboratory for 35 years now, so I kind of grew up there. Started out there when I was only 19 years old, so I've been there a couple of days. I graduated from a local university, Idaho State University, back in '98. My background is in electrical engineering. I manage a group of 15 engineers and 4 technicians. And our mission, if you want to go to the next slide, our mission is to fuel, test, and deliver these radioisotope power systems and related technologies for use in remote, harsh environments such as space. And I'm going to be talking to you about a couple of missions that I've worked on personally and that are near and dear to my heart, and also some upcoming missions and upcoming technologies that we are involved with. Now, I work in the Space Nuclear Power and Isotope Technologies division, and division-wide, we are about 70 employees.
So with us there, Kelly? Might be having some technical difficulties for a moment. She'll come back in a sec. While we're waiting for Kelly to get back online, throughout the presentation, if there are any questions for Kelly, you can either use the raised hand option in Zoom, or you can just send me a private message or a message to the whole group in the chat option, and we'll make sure that we get those questions answered. Looks like Kelly is going to log back in a moment for us, and then we can keep going. There she is.
Ah, I think
Welcome
I'm back. Wow, I have no idea what happened there. Did you guys just turn me off? Are you bored already? Wow. Okay. Okay, let me get my screen back to where I was at.
All right.
Okay, sorry about that.
No problem.
Hopefully I won't do that again. Okay, so these radioisotope power systems, you see a couple of illustrations there at the top of the screen. These are nuclear power systems, and they have radioactive fuel inside of them that generate heat. And that heat is converted into electricity. And I'm going to speak to you about a couple of different styles of RTGs. We call them radioisotope thermoelectric generators. And that radioactive fuel that is in them is a ceramic plutonium oxide pellet. And I've got some pictures of those. Next slide. So radioisotope missions number just in the tens. Even though the program enjoys about a 60-year history now, there have not been tons of RTG missions, but here are a few. And this just illustrates those deep space missions where we have provided nuclear power to run instrumentation on spacecrafts, or maybe even the mobility of rovers. And I'm going to talk about a couple of rovers in particular. So we've been all over the universe, to the poles of the sun, and now out past Pluto and into the Kuiper Belt. Next slide. So what are thermoelectric devices? It is an electric circuit composed of materials with different Seebeck coefficients. So basically you have dissimilar metals, very similar to thermocouples. And if you apply heat to one side of that semiconductor and cold to the other side, you have a temperature difference. And you see in this illustration, there are some module bars down here at the bottom. I think, can you see my cursor?
Yes.
Okay, thank you. So these are the module bars, and these module bars would contain these thermoelectric circuits. So this picture depicts a 125 watt electrical output nuclear power system. So you have the heat generated from the fuel that's inside the internal cavity of the RTG, and then you have the coldness of space on the outside, and that's creating your temperature difference. And it doesn't do this very efficiently. They're only about 5 or 6% efficient, but they work where the sun doesn't shine. And so that's why we have these, and they are utilized for those deep space missions. Next slide. Okay, so just a little bit about the agencies that work with this material. We certainly are not a one laboratory band. The Department of Energy, Office of Nuclear Energy, actually has a program called the Continuous Rate Production Supply Chain. And we work with other national laboratories in order to produce this radioactive material, assemble the power systems, and deliver them down to Kennedy Space Center in order to support space launches and deep space missions for them. So I'm just going to start in the upper left-hand corner here. And Oak Ridge National Laboratory is part of the supply chain there in Oak Ridge, Tennessee. And they actually supply the isotope, the Pu-238 isotope. They make that isotope from neptunium. They build what are called neptunium targets, and you see a target right here in this picture. It's kind of a yellowish cast and a long cylinder here. That's a neptunium target. Those have literally pellets in them, small, very small diameter pellets, and hundreds of them. They are inserted in that assembly, and then that assembly is inserted into one of two reactors. The HIFER reactor at Oak Ridge National Laboratory, and also there are targets inserted into the Advanced Test Reactor at INL. Those they're inserted into the reactor, and in those particular reactors, when they go critical, meaning they're generating power, they also in turn create a neutron flux. Anyway, that energy from the neutron flux bombards the neptunium isotope, which is also radioactive, causing a chain reaction. And subsequently, if you leave it in there long enough for maybe, say, 6 months of time, you will end up creating an event changing the neptunium into the plutonium-238. Those targets are then shipped back to Oak Ridge National Laboratory, and they take those pellets out. Now they have pure Pu-238 isotope, and then they add things to that isotope to make the plutonium-238 oxide fuel. Then that oxide fuel, which is in a powder form, is shipped to Los Alamos National Laboratory. Los Alamos National Laboratory makes pellets out of those. They're ceramic pellets out of that Pu-238 oxide powder. And you see a ceramic fuel pellet over here to the right. That is a bare pellet. And that pellet is inserted into this iridium cladding. That iridium cladding is also manufactured by Oak Ridge National Laboratory. And you can see pretty clearly in this picture here, there is a weld around the center. We call it a girth weld. So this cladding comes to Los Alamos National Laboratory in two pieces. So then you would place the bottom of the cylinder inside a glove box, inside an argon environment, and you would put the pellet in the bottom cylinder, part of the cylinder, put the top of the cylinder on, and then weld around the middle or the girth of that pellet. Now, or of that cladding material of iridium. Now that, just to get a size in mind, this is about 2 inches tall and about 2 inches in diameter, and it's a cylinder. So then once those fuel clads are made, they are sent to Idaho National Laboratory. And that's what you see down here in this picture. In these red glowing pictures, we insert 2 fuel clads into graphite impact shells. And those are graphite, and we call them, we refer to them a lot as salt and pepper shakers. So they're about that size, you know, they're not very tall, they're about a little over 3 inches tall, and each of them hold 2 of those fuel clad pellets from Los Alamos National Laboratory. Then we insert a stack of these into these power systems. You see a power system that's fueled there with the white fins on the bottom left. And then after we do some fueling and testing, we send the power system down to, or we actually ship it ourselves. I'm sorry?
Sorry, mistake.
Everybody okay?
Yeah, we're good.
Okay, great. And after we fuel and test our power system, we deliver it down to Kennedy Space Center for the launch. And here you see a picture of an Atlas V rocket. And inside the fairing, which is the white part at the top, you would find our power system. So I have some more close-up pictures of these things, but I'm going to describe to you in a little more detail about where we do these activities and a little closer up pictures of what things look like. So next slide. These are some photographs taken at Kennedy Space Center. The one in the upper left-hand corner is an actual photograph of the spacecraft New Horizons. It was the first space mission that we were involved in providing the power system from the INL. Before the program was moved to Idaho National Laboratory back in 2002, it resided at the Mound Complex in Miamisburg, Ohio. It was moved after 9/11 to Idaho because we had the security force to be able to better protect, in the Department of Energy's eyes, the radioactive fuel. And quite frankly, it's why we're involved, is because we can handle the fuel. We have that expertise. So this is the spacecraft here, and you see the power system cantilever to the side. It's the black cylinder. And here is the black cylinder, or the black power system that you see here to the right, sitting in the vertical position. And it's in a storage base that we use to transport it inside buildings. So this is a 300-watt class system, and you see some vital statistics here. And I'm going to just draw your attention to the other picture down here. This is our most recent one. It will be powering a land rover that's going to Mars to launch in July of this year. So we have it down at Kennedy Space Center, and this is a picture of the facility that we do one of the 3 facilities that we do our work in. So here you see the power system. It's called a multi-mission radioisotope thermoelectric generator. I like to say that's why we have acronyms, because that's kind of a mouthful. But this one generates 125 watts of electricity. So neither of these provide a lot of electricity, but enough to power, in this case, the white one here. It powers all of the instrumentation on board the Land Rover, and also powers the all of the motors that operate the rover itself and make it move across the Martian surface. So you see some of the vital statistics of each of these. The MMRTG, we were the first ones to fuel and test this particular series of power system. And we supported the Mars Science Laboratory, which is a land rover that went to Mars. It launched in 2011, and it has one of these units on it. And now again, the Mars 2020 land rover that was just recently named Perseverance. And it will also contain just one of these power systems. The general purpose heat source RTG that powers New Horizons, as I said, it's a 300 class system. This one, beginning of mission power, was 250 watts. And they're just comprised of different unicouple materials for the thermocouples. Remember that Seebeck effect I talked about? These were made of silicone germanium unicouples, and the thermoelectrics in the MSL and Perseverance rovers are lead telluride tags. So different materials work better for different temperature ranges and for different applications. And you kind of get a feel for the size of these. So this is me here with my team here. And if you didn't notice me, I'm the cute second one from the right here. So these aren't extremely big vessels, not to mention not large power systems in a physical size. They only weigh right around nominally 100 pounds. GPHS is 127 pounds, and the MMRTG is only 97 pounds. Next slide. So where do we do this work, and what are our capabilities? So we work in several different facilities, locally to Idaho and remotely. Kennedy Space Center, namely, is what I want to talk about today. So if you go out to our desert site, you could come to Idaho Falls and then head towards Arco, if anyone's familiar with the landscape around here. and about a third of the way out, or about 30 miles outside of Idaho Falls, you would come to the INL Materials and Fuels Complex. And here's an aerial view of it. And you see this little spacecraft looking building. Well, that's not our building. I think it should be our building because of the shape of it, but our building, our nuclear facility, is this building right in front of it. And if you were to blow that building up, it looks like this. This building in the front is an office building. It's the nuclear facility where we do our work, and I'm going to show you pictures in subsequent slides of the equipment that we have in there to do our work. We also do work at the Engineering Development Laboratory. You see from the aerial view, it's back here. A close-up picture of it down here is where we do our non-radioactive work, and we have tons of it that we do as well. Now, when we go down to Kennedy Space Center and take our power system down there, we do that in a semi-truck. And I'll show you some pictures of it in later slides. My point about working remotely is that when we take our power system down, we work in 3 different facilities, 2 at Kennedy Space Center and 1 facility at Cape Canaveral Air Force Station. Now, when we take our power system in there, remember it's still a nuclear payload, and we have to declare those facilities nuclear facilities. So while that's all a nice, neat package to say, there's just a lot of safety rigor that goes in with declaring them nuclear facilities, and also the rigor that we go through to perform work using radioactive material. So I'm going to talk a little bit about those things and then the capabilities inside our nuclear facility. Next slide, please. So the first thing, one of the first things that the 3 things that we have to do is that we have to have is the radioactive fuel. We have to have the power system that's unfueled, and we have to have all of our equipment ready and people trained in order to do this work. So pictures that you see here is a cask in the upper right-hand corner, and inside this bird cage, which protects people from the heat, you would see a cylinder in the middle of it. Inside that cylinder that has a bolted closure, you would find another cylinder that's welded, and inside of it is another cylinder that's welded, and inside that you would find some smaller cylinders that contain the fuel. Yes.
Hey Mom, what are you doing?
So this is how we receive our fuel, and you see nuclear facility operators here that are moving it into the facility. You see an operator here that actually chucks up this a cylinder that's inside this one. It's a stainless steel cylinder, and he literally is using a giant pipe cutter in order to cut that containment vessel open. And then again, inside of it will be a liner that's stainless steel, and inside of that would be product cans. Each of the product cans would hold 2 of these fuel clads. So here you see a picture of the pellet, so glowing red hot, and that pellet would be inside this iridium cladding. And this is the form that we handle it in at the INL. This ceramic pellet form is the form that Los Alamos National Laboratory handles it in, and it's what they make out of powder material. Okay, next slide. Okay, so we assemble these fuel clads in what are called general purpose heat sources. So you see an illustration at the bottom left-hand corner of the general purpose heat sources. They're about 4 inches cubed in size. And you see the assembly here. The red indicates those fuel clads that we saw in the last slide. And 2 of those fuel clads are inserted inside a graphite impact shell. And then 2 of the graphite impact shells are inserted inside the general purpose heat source. Now these are actual pictures during the fueling process that you see in this picture. And then in this picture, you see one that is completely fueled. Now, we do this work inside a glove box for a couple of reasons. Okay, so if you've not seen a glove box before, perhaps you've been to a hospital and you've seen in ICU, perhaps because when my daughter was born, she got to be placed into a glove box and she had black lights put on her because she was jaundiced and she wasn't eating, and anyway she was in there. So I got to see a human in a glove box, which I don't really care to see, but a glove box very similar to it is used for our fueling process. So you see plastic gloves here, you see plastic windows up here, and then this is a metal steel frame that they're in. Now inside this glove box, you would have an argon atmosphere. We have argon in there because we do not want the graphite parts to oxidize, because you want a good heat transfer path from the heat of the radioactive material to those thermocouples that I was talking about. Remember the hot side of those thermocouples? You want that to be as hot as it can be. So again, we place 4 of these fuel clads inside each of these heat sources, and then we stack those, and I'll show you that picture next. But before we move on, you see here in this far right-hand lower corner picture, a fuel clad being inspected. The gentleman holding the flashlight is a quality control inspector, and he's actually reading serial numbers. It's about a 200-page procedure that we use to assemble each of these general purpose heat sources. So a lot of rigor goes into these. Literally a step is read. An operator will repeat back what he is supposed to perform. The reader will say, yep, that's what I want you to do. Then the operator will perform the step, and then they will go to the next step. So it takes us an entire 14-hour shift without any issues to stop work in order to assemble 4 fuel clads into one of these general purpose heat sources. Next slide. So I mentioned the power system itself. So the power system is what converts that heat into electricity, and those are manufactured by private industry. This particular one was designed by Teledyne Energy Systems Incorporated out of Huntsville, Maryland, and it was built and tested with electric heaters in it in Pasadena, California by a company called Aerojet Rocketdyne. And once they get finished with that testing, they ship it to Idaho National Laboratory so we can put radioactive fuel in it. And so you see operators here putting some equipment on the top of it so that we can lift it out of its shipping container and put it on this intra-building transfer cart. And that's what you see in the lower picture here. Next slide. And then it is moved into a little hot cell chamber that you see in the lower left-hand corner. It's called an inert atmosphere and assembly chamber. And the power system you see in the center bottom picture, you see it being inserted into that chamber. Then, and you also see it being inserted in the lower right-hand picture also. In the top picture here, you see the data acquisition system, and you see operators looking intently on a screen. So you see my lead technical engineer, he's my project engineer. You see and you see 3 operators here. They run this equipment, and this data acquisition system is electrically connected to the power system, and the power system health is monitored the entire time that it is being fueled. So we're making sure that the temperature does not increase beyond a certain rate of time as the fuel's being inserted into it, and we're checking to see what power it is producing as we're fueling it. You'll see a lead engineer over here. That's our Brandon Horkley. He's the lead engineer over the data acquisition system. And then you see a quality control inspector, Abby, behind him. So you can see there's a lot of people overseeing the work and performing it, and that are responsible for the execution of it. So if you go to the next slide. Okay, in this slide, you actually see a stack of 8 of those general purpose heat sources in the left-hand picture. Okay, so those are stacked on what is called the stacking fixture, because we're engineers and we kind of don't have crazy, brilliant names for things. But you see that stacking fixture here. You see some tubing maybe back here in the background. And there's water running through that tubing. So this is very hot. This is about 2,000 watts of thermal energy that's being produced by this stack of fuel. Each of these modules separately are 500 degrees Fahrenheit at the surface at this point. And they are stacked up, and then they are lifted by a hoist inside of that chamber, and they are lowered slowly into the center cavity of the power system. And that's what you see in the upper and lower right-hand pictures, is that fuel stack being lowered. It's lowered at a 1/2 inch every 30 minutes. So it's lowered very slowly. And again, you just see a picture of the fuel clad just as a reminder of what's generating all that heat. Next slide. So once it gets fueled, and it takes us about 30 days to get the fuel inside of it, we put insulation around it. We put graphite in pieces on either side of that stack. We compress it to about 4,800 pounds with a compression tool. And then we we put a lid on it and then fill it with helium, and then we weld up that little port that we use to put the helium inside that central cavity. So it does take quite a long time, in my opinion, to put that fuel stack in there. So this is a fueled unit that you see here. So it's now generating 125 watts of electricity. And you see a nuclear facility operator here, and he's taking some electrical measurements of the power system now that it's out of the IAC. And you see some plastic parts right here. The plastic that's actually shielding. So that shielding is protecting the worker from the radiation that's being generated from the power system. Next slide. Okay, so once we get it fueled, we put it through a suite of acceptance tests. I'm not sure why the highlighting is here. I must be doing that, huh? Sorry about that. Somehow my cursor decided it had color maybe. So this is, again, the fueled unit, and we put it through a suite of acceptance tests. Those acceptance tests are designed to put the power system through environments that it will see during the life of its mission. So this is vibration testing equipment that you see here, and the power system is placed on it. This shaker table is energized, and it excites movement, imitating the environment that it would see on the launch pad, and then on entry, descent, and landing on the Martian surface. You see the control room and the operators here. This control room is in an adjacent room to the vibration testing equipment, and they control the excitation of the vibration equipment from this control room. So they put it through the tests, excite that table, put it through a bunch of different tests, and it takes us about 20 days to perform the testing in this station. Next slide. Once it gets through vibration testing, we send it over to mass properties testing. And you see that it is placed in a fixture here. It is rotated 90 degrees. And so in 2 different orientations, this particular equipment measures the center of gravity and the moment of inertia. So the entire spacecraft and the land rover will move to Mars as one piece. And you want that entire system to be balanced as it's going through space so that we can receive signals through the space network back to Earth, and so that we can control whatever movements need to be made to adjust the attenuation and the profile of how that spacecraft is maneuvering through space. So this is just one of the things that we do to provide NASA with that information so that they can have a balanced system, because they literally put the spacecraft with the rover inside of it on a spin table and spin balance it like you would a tire. But we don't allow them to spin a nuclear power system. So they use a mass model on their spacecraft and on the land rover in order to simulate the nuclear power system. And then we provide the center of gravity and moment of inertia just as confirmatory information that, yep, this is the same as your mass simulator and it will respond the same. Next slide. This is magnetics testing station. Again, we put it in a different fixture. You see the MMRTG there, and we do an electromagnetic mapping. So it is generating DC power, and it is also generating an electromagnetic signal. Now, oftentimes you want to measure the magnetic signal in space or to a planet that you're going to investigate, and you don't want to be measuring what you're generating. So we just want to know what we're generating so it can be filtered off of onboard instrumentations of the spacecraft or on whatever it's powering. Next slide. And then lastly is thermal vacuum testing. And I am sure this is the most important test that's done, perhaps because I was once the subject matter expert and the test engineer over this piece of equipment. It was one of my very first jobs in this program. So while I'm sure it's the most important one, it actually is the last test that we do. And we put it in this chamber and we draw a vacuum on it. And we just simply measure the power output just to make sure that, hey, we've put it together, it's survived all of its acceptance tests, and we just want to put it in a vacuum and see and make sure that it's generating the power that it was designed to power. So I thought this was a really big vacuum chamber, having seen other vacuum chambers at INL in our analytical lab, which measure like maybe a foot tall, maybe a foot square chamber. So I thought this one was really big. It's 6 feet in diameter and 9 feet long. And so thinking that I was in charge of some pretty spectacular and large equipment, and it turns out I was even more naive than I thought I was, I went to the Jet Propulsion Laboratory. Now and I saw their vacuum chamber. So while we can simulate near-Earth vacuum of space, and we can simulate the coldness of space, I went down to the Jet Propulsion Laboratory. They have a building, and the only piece of test equipment in it is a vacuum chamber. It is a silo, and it is 25 feet in diameter and 80 feet tall. And they not only simulate the vacuum of space, not near-Earth space, so they pull a larger vacuum than I can, and they simulate the coldness of space. They also simulate the sun, so they have quite a light fixture that they hang in the top of their silo to simulate the sun as well. So I came back very humbled from the Jet Propulsion Laboratory. Next slide, please. Okay, so since we're a full service laboratory, once we fuel and test your power system, we will deliver it to wherever you want to launch from, in this case, Kennedy Space Center and Cape Canaveral Air Force Station. So that's what you see here. On the left picture, just to the right of the inset picture there, you see a cylinder there behind a net. That is our 9904 cask, and that is how we transport our nuclear power systems over the highway. So this is a Department of Transportation certified cask. It is 2 steel nested cylinders that are nested one inside of the other. You see at the RTG facility down at Kennedy Space Center, this center picture where we're disassembling the cask. And inside of it, once you get the 2 bells off of it, inside of this white base unit down here that you can see separated, it would contain the nuclear power system sitting vertically in that base. We can transport 2 of these casks inside our specialty transportation trailers. These come equipped with not only the ability to hold the cask, but also 2 diesel generators to provide power to the instrumentation, the cooling systems, and the data acquisition system that is inside the instrumentation compartment inside this transportation trailer. Now you see a Kennedy Space Center tractor pulling it right here, and you see the RTG facility in the background there. Now when we actually pull the trailer over the road, the Office of Secure Transport, which is a DOE agency, and there are a lot of guys with guns and tattoos, is how I describe them. They actually convoy and protect this nuclear payload as it is transported across the United States to Kennedy Space Center. I do provide a 6-person technical team that accompanies the guys with the guns down to Florida. And that team is, we call them the chase team, and their task is to respond to any emergency or any abnormal conditions that may happen as it's transported across the United States. Up in the upper right-hand corner, you see a picture of Space Launch Complex 41, Slick 41 there. It is on the Atlantic coast. You can see from the top of this building, which this is a close-up picture of this building that you see in the background. And you certainly can see the ocean from the top of that building. The spacecraft is actually stacked in this vertical integration facility, is the name of this building. It is stacked, and the fairing is then stacked on top of the rocket after it is assembled and fueled. Inside of this fairing would be the spacecraft. Inside the spacecraft would be the land rover, and it would be upside down. And about launch minus 9 days, we bring over our nuclear power system. So we transport it in this trailer over to Cape Canaveral Air Force Station, and we hoist it up about 200 feet on the outside of the building, land it on this mezzanine floor, the highest one that you can see here. It's about 200 feet up. And the power system is installed on this RTG insertion cart. And you see the RTG back here in the background, and you see it on this big lever arm right here. So this is rolled in upside alongside the fairing on this mezzanine floor up here, and it would be inserted through a 6-foot fairing door, through a door on the spacecraft, and attached mechanically through a special adapter to the land rover. and then it is electrically connected as well. And then tests are done to make sure all systems are operating, the RTG is connected, and the rover systems are functioning. And then that fairing door is closed. And this rocket is moved by rail out to the center of this launch pad. Let's see. Okay. Okay, do you want to go to the next slide? Okay, so here's a picture of the rocket being transported out to the launch pad. So this particular one is of the Curiosity rover launch in 2011, but the Mars rover Perseverance, it will be on the same launch vehicle. It's an Atlas V. It has one rocket engine at the bottom of it that you can't see. You see some solid rocket boosters that are those pencil-looking white things on the side. There are 5 of those. And then the fairing that you see that takes up as much as the rocket space there at the top. Okay, so you see it being moved out to the center of the launch pad. It's moved to the launch pad about launch minus 3 days, and that's where it will sit until we are go for launch. So let me tell you a little bit more about the other pictures here. So these are pictures of the rover that we will be powering for this mission. So this is a picture of the rover, and the rover is in the upper left-hand corner, and you can see the wheels. They're wrapped in Kapton tape, and they're being the rover's upside down, and you can see the entry, or what you see above it is the entry, descent, and landing apparatus that will be attached to it by 4 cables. This is what will literally lower it to the Martian surface on 4 steel cables. And after it is lowered to the surface, those 4 cables will be severed by pyrotechnic devices that are installed on each of those cables. I thought it was kind of interesting on this rover. There was a time where you could send your name to Mars. There was a campaign to do that. And so this particular module is carrying the names of 10 million people throughout the world. And those names are etched onto 3 microchips. So that was a picture that was taken in March of 2020. And then the picture on the upper right-hand corner is a picture of the booster being delivered for the rover as it's being offloaded from this cargo aircraft at Cape Canaveral Air Force Station. So a lot of different agencies and companies are used to perform this work. So please don't come away with this thinking that INL is the only player in this game. We are a small portion, albeit I believe we're important part of the mission, because we're providing the power for the rover and all of its instrumentation. But oh my goodness, there are a lot of people involved in making this successful. You see the names up here. Before Mars 2020 was named, these were some options, and there was a worldwide contest that you could submit. Kindergarten through 12th grade kids could submit a paper justifying or telling us what the name was that they would like to name it and why they wanted to name it that. And so these were some of the names that they came up with, and then the vote went out, they were down selected, and then NASA picked one of those names, and they happened to pick Perseverance. Okay, next slide. Okay, so This is a slide that just depicts another activity that we perform at Kennedy Space Center. This is a picture at the Payload Hazardous Servicing Facility. And this is a clean room facility. The center picture here is really exciting for us because it's the first time that the nuclear power system fueled is going to power the land rover. The rover is tested with an electrically powered power system, so it has electric heaters in it instead of radioactive fuel, and it's tested quite a bit using that simulator, but this is the first time we'll see it powered up. So we put our RTG into this transportation trailer, and that's what you see on the bottom left here. We put that in our truck, and then we take our truck over to the Payload Hazardous Servicing Facility, and that's what you see in the far upper right-hand corner. And in the bottom right-hand corner, you see again a closer picture of that insertion cart that you saw in the previous slide of the RTG being inserted into, and it will be mated here electrically and mechanically and tested in this clean room facility. So you see these folks are all dressed out in clean room suits, lovingly referred to as bunny suits. So it's pretty warm to work in these all day. And of course they have masks, and this is all made of Tyvek material. And then these other two pictures are just a reminder that this is where the power system was being stored, was in the RTG facility. So you see the fences around here, there's a security post. So when we declare these facilities nuclear, we have a security force that accompanies us as well. So next slide. Oh, whoops. Okay. So what is left for INL to do? We are just awaiting the fairing containing the rover and the spacecraft to be moved over to Cape Canaveral Air Force Station and put on top of that rocket. They're a little bit behind schedule right now. The launch has already been delayed 3 days, and they had some issues with the booster that you saw a picture of it, and I don't know what the details were with it, but they got that ironed out, and then they're just a couple of days behind at the Payload Hazardous Servicing Facility, where they're encapsulating the spacecraft into the fairing, and those are the pictures that you see here. So they're a couple of days behind there. So I think we're going to end up seeing another delay for a total of 5 days. The launch window opens July 17th, and it lasts through August 5th. And so I think our first opportunity for launch now is going to be July 22nd. And it'll be 9:35 Eastern time. There's a 2-hour window each day, and it'll start on that day. And if weather is cooperating and all systems are go, we'll get a green light and be able to launch. The pictures you see here are an aerial of that clean room facility, the Payload Hazardous Servicing Facility. You see a picture of the Land Rover when it was just being delivered. So it had just been delivered to this facility, and it's unfolded and it's perky and it's standing upright, and it's going to start. They're going to start system testing on it. And then to the right here, you see a picture of a bigger over an aerial of the clean room. So you see the spacecraft that's back here. And then in front, you see the Land Rover that's upside down. And then you see the entry, landing, and descent stage that's going to be put on top of it. This, you see it all in here. So this is how it's going to look compacted, and this is going to be placed inside the spacecraft. And then finally, the spacecraft will be encapsulated inside of this fairing. It'll be closed up. It'll be hoisted to a horizontal position, and then they'll take it by flatbed truck over to Cape Canaveral Air Force Station and hoist it up and assemble it, and hoist it up and place it right on top of the rocket. Next slide. Okay, this is a closer view of the work that we assist the Jet Propulsion Laboratory in. I should give a shout out to the Jet Propulsion Laboratory. I mean, it's their mission. They are a prime contractor for NASA. They are the ones that designed the land rover and organized all of the scientists and the scientific instruments that would go on it. So there are a lot of Jet Propulsion Laboratory employees down at Cape Canaveral Air Force Station now trying to stay COVID-free and get everything assembled to take over to Cape Canaveral Air Force Station. This middle picture here just depicts a view of that hoist up to that 200-foot level mezzanine. So unfortunately, it's not a great picture, but this label here is where the MMRTG is. You see some lines coming down here. These are tag lines. So there are people on the ground level that are manning those tag lines. But this just kind of shows a different view of it being hoisted up there. And then you see it landing up here again, these tag lines, and then you see the MMRTG way up here. It'll be disassembled out of this caged assembly that it's being hoisted up with. And then the power system will be placed on this cart. You see another picture of it, and that's what will be used to insert it through the fairing door that's on this level right here. So it's hoisted down from this level to this level and inside that fairing door. Next slide, please. Okay, so hey, we're gonna launch as I indicated in July. Hopefully we'll get there, and it looks like we're going to be a go. But this picture you see over to the left here is just a picture of the launch sites at Cape Canaveral Air Force Station. And you literally can get on a Google map and put in SLC 4040. For some reason, 41 won't take you there, but 40 is right next door to it. And yeah, it'll give you directions on how to get there. The center picture is a picture of the launch for the Mars Science Laboratory, Curiosity. And then you see some illustrations over here to the right of the spacecraft traveling through space, and then an illustration of that entry, landing, and descent stage, lowering the rover down to the surface. And then the bottom picture is actually a selfie. It's a collage of several, of many pictures that was taken of the Curiosity rover. Next slide. Okay, so the Mars 2020 mission is the second of 3 missions. The first mission was Curiosity. The first of this New Frontiers mission was Curiosity. It was sent to Mars to investigate the Martian surface and find any evidence that it was habitable for microbial life. Said evidence was found. This mission contains stainless steel tubes on the bottom of the carriage, and it will collect soil samples. And then there will be a third sample return mission so that those soil samples can be brought back to Earth for further examination. Next slide. New Horizons, it's still out there roaming around. It launched in January of 2006, a 9.5 year voyage. It flew by its closest encounter, Pluto. You see that in the second picture there. That was the first picture that was sent back to Earth, and as luck would have it, there was a heart shape of methane gas. So that was definitely a cool picture to have sent back. It continued on out into the Kuiper Belt, and on New Year's Day of 2019 sent back some pictures of its Kuiper Belt object that was named Ultima Thule. And then it also sent back, there's also some pictures of Pluto and one of its moons, Charon. Now, you know, lots of controversy over whether or not Pluto is a planet. It's now considered a dwarf planet, and the axis of rotation is actually in the center between Pluto and its moon, Charon. Next slide. Mars Science Laboratory Curiosity, it too is still sending back data. It just reached probably the highest peak that it will climb and go over. You see a picture, a selfie of it there, right before it was going to climb to its highest elevation. You know, we have pretty high mountains around here, and not that there aren't high mountains on Mars, but I think 11 feet, it was about 11 feet below the point where it was going to climb over that little mountain that you see there. So it's still roving around, and it's sending us back data to date. Certainly the power system, you see it circled in red, it's still operating all of the systems on the rover. So looks like she could use a car wash for sure, though. She looks pretty dusty. And then next slide, please. So where are we going next? Our next space mission, as far as RTG goes, has been identified as Dragonfly. It will be a multi-rotor helicopter, and it will be going to one of the Saturn moons, Titan. Launch date in 2026. But another spacecraft called Cassini-Huygens, which you may have heard about. It was launched in 1997. It had investigated Saturn, and as a result of its investigations, and that spacecraft was powered by 3 RTGs, but for a total of 900 watts of electrical power. But as a result of its investigation, NASA decided it wanted to go to the Titan moon and investigate there. So this rotorcraft will be powered by another MMRTG, and we just put in a contract with Aerojet Rocketdyne to build another one for this particular mission. Now, if you haven't heard about the Curiosity and Mars 2020 landing, the landing is from that sky crane, that entry, descent, and landing apparatus that I talked about. If you get the opportunity, you should go online and just Google 7 minutes of terror. And you will see a 7-minute illustration of how the spacecraft enters the Martian atmosphere and how it ends up being slowed down and lowered to the Martian surface. I got the opportunity to hear Jason Barnes, the U of I principal investigator, talk about the landing on Titan. And so he made this statement in comparison to the 7 minutes of terror. He says, yeah, this one will only be an hour and a half of mild concern versus that 7 minutes of terror. So much heavier atmosphere on the Titan moon. As a comparison that he gave was, if you were able to stand on Titan and flap your arms, you would fly. The atmosphere is that thick. Versus Mars, that has a very thin atmosphere. There is a helicopter on board the Mars 2020 rover, and it will be deployed. It has a 6-foot single rotor that rotates at 3,600 RPMs, and they just want to see if they can fly a helicopter there for maybe in use in bringing those samples back to Earth. Next slide. A few other things that we're involved in, and I'll just kind of quickly touch on these, is nuclear power fission systems and nuclear thermal propulsion. And that's what the next two slides are about. But reactors in space. Reactors are needed to provide power for colonizing the moon and eventually Mars. So we are involved in the development of those nuclear reactors. Next slide. And and this is a slide a little more detail about the surface fission power and the reactor design. We're working in cooperation again with Los Alamos National Laboratory, Idaho National Laboratory, Oak Ridge National Laboratory, private industry, and BWXT for the surface power fission. And then the next slide, please. And also nuclear thermal propulsion. So NASA also wants to build a reactor that can generate enough heat to heat a hydrogen propellant through space. So you want enough power to get a payload or astronauts to Mars more quickly than the 9-month voyage that it currently takes the spacecraft to get from Earth to Mars now. So development's going there, working in cooperation with all of those agencies and private companies that I mentioned. Next slide. Just another slide on nuclear thermal propulsion, and you guys have the slide, so in the name of time, since I have talked forever now, we'll just go on to the next slide. This is a slide dedicated to that PU-238 fuel services program. And I talked about we make PU-238 in the reactors. This is a neptunium target here. That's what the neptunium would be in, and that whole target would be inserted into a reactor. And these are just closer up pictures. Okay, next slide, please. And finally, lastly, I'll give you guys a chance to ask questions if you would like. You can certainly follow us on social media. I would encourage you to a couple of places where I just could spend my entire life investigating. Nasa.gov/missions will take you to all of the missions, not only the nuclear missions that NASA is funding and following right now. They have a fabulous, fabulous website if you are a space junkie by any means, and I would think that the folks in this community are.
I think we might have lost her again. Hopefully she'll come back in a moment and we can thank her for giving that awesome presentation, and we can then do some Q&A. My guess is whatever happened the first time at the beginning of her talk just happened again, so it'll probably just be a few moments until she reconnects to the internet. And if Kelly can't join us again, we'll just go right into the door prizes and raffle prizes. We'll just give her another minute here. Here she comes. Hi, Kelly. Oh, we can't hear you yet. Still can't hear you.
Oh, can you hear me now?
There we go.
Okay. Wow. Okay, good. You didn't turn me off again. I was afraid you would turn me off.
Nope, we waited for you.
It's so hard to give these huge virtual presentations because you can't tell if everybody fell asleep or, you know.
Now we're all still here. Well, thank you so much for that great presentation. We'll do some Q&A now. And yeah, if anybody has any questions for Kelly, please go ahead and unmute yourself and you can ask your question.
So, do you know how many rovers are out on other planets and moons?
I don't know the total number. I can speak a little bit towards Mars. There is a Mars exploration program that NASA funds, and there are several rovers up there. There are only 2 nuclear-powered rovers up there. Well, the second one's going up there. So the only nuclear-powered rover is Mars Science Laboratory Curiosity, and it will be joined by its sister Perseverance. But they number in tens. Just on Mars alone, there are probably, I would guess, around 30-ish represented by several different countries.
That's a great question. I feel like I should know the answer to that, like the total number of space probes on other worlds. I'm going to look that up and I will post it on our website and our blog tomorrow.
It is a great question.
I wish I knew the answer, but I'll find out and post it on the blog tomorrow.
Awesome. Anything else?
Well, I've got a question for you, Kelly. So near the beginning of your presentation, you mentioned a couple of different gases, both argon gas and helium, used in different applications. And I was curious about why argon gas in one application and why helium gas in another.
Sure. So the argon is used when we assemble the fuel clads into the graphite aeroshells. So all of those components that the fuel clads go into are made out of a specialty graphite. It's called finely pierced fabric, and it was used by the Department of Defense on nose cones of missiles. So at high temperatures, high thermal temperatures, it's very, very strong material. So all of those components that encapsulate the fuel clads were designed for safety. So if the power system should re-enter the Earth's atmosphere during a gravitational assist around Earth, or just a launch pad accident, or for whatever reason, that aeroshell is designed to be able to re-enter the Earth's atmosphere, ablate, which means some of the material would be burned off because of the heat of the re-entry into Earth. And be able to hit concrete at terminal velocity and still withstand that event. So that's why those materials are used. The reason we use argon to assemble it is so that graphite material doesn't oxidize, because that causes the heat transfer to be less and also deteriorates the graphite material. Now, helium is inserted in the central cavity because while we utilize the heat that's generated by the radioactive decay of the material to convert it into electricity, there's other things going on with that fuel clad. It is generating helium, for one. It's also giving off energy in the form of radiation. But it generates helium. That helium escapes through a little frit vent that's in the top of those fuel clads. And the reason there's a little vent in the top of it is to allow that gas to escape so the iridium cladding does not expand under pressurization of too much helium buildup in there. So that helium is released from the fuel clads out through the aeroshell, the graphite material, and into that central cavity. So helium is also placed in that cavity because you want to keep a positive pressure inside that central cavity, because you're going to put it in the vacuum of space. So if you didn't have anything in that cavity, it's designed such that helium is going to be generated. It's going to keep a certain pressure in there, and then the vacuum of space won't damage that cylinder that all that fuel's in. And then there's a gasket that literally is designed to dissipate the helium buildup inside that central cavity at a specific rate. So it's always generating helium, and then the power system itself is always releasing helium. Small amounts, but still.
Got it.
That was,
Thanks for that.
that was a long-winded answer.
No,
Sorry.
good. So the argon is just like an inert gas, right?
It is. Yes.
And so could any inert gas be used, or is argon just like the easiest or cheapest inert gas? Or
Yeah, any inert gas could be used. I mean, its properties, a lot, we're dealing with heat. So we, another thing that it allows, it's because it's inert, it's not going to create an environment like oxygen would that would be help a fire, so we're putting like a 900-degree fuel clad inside a box with plastic windows, and we're using plastic gloves to hold stainless steel tools to handle them with. So the inert gas helps there too.
got it.
Mm-hmm.
Any other questions for Kelly? There are a couple in the chat, but I think you actually you answered the one. One was a question about
You have the video off, so they can't see.
About what would potentially be the dangers of a failed launch with plutonium-238 on board. But you just talked about that in answering the other question.
I did, and there is the NNSA, the National Nuclear Security Agency. They actually are deployed at Cape Canaveral Air Force Station, and they train a team comprised of many people. And I actually have an engineer that's on that team, and his job would be to go out and identify piece parts of our nuclear power system should there be some kind of accident. So they literally provide the workforce and the equipment that would be needed to pick up all of the pieces of the rocket and whatnot. For nuclear launches, you can't get as close to those as you could a manned mission when it launches. So there's some extra rigor involved there, and counties that could be affected by a nuclear accident are all involved in the launch approval process.
Cool.
Kelly, I have a question. What is the projected lifespan of the power source?
Oh, excellent question. So the Pu-238 oxide half-life is 87 years. So that means the half-life at half of it will be producing half of its energy in 87 years. So it will last a very long time. So as long as the system is together, and it will be generating power. Now the thermoelectrics are going to be the first thing that are going to degrade, because the heat makes those thermoelectric materials degrade. So so that's just going to happen. That's how it works. But Voyagers 1 and 2 were launched in 1977 and 77 or 78, sometime in that time frame. And those were powered by nuclear power systems of similar design. And they are still sending data back to Earth. NASA is still collecting that data. So a very long time, decades. NASA will get bored with the data before they quit sending power.
Thank you.
You're welcome.
I've got another question if somebody else doesn't. Oh, please go ahead.
So if wait, does NASA use, or do you guys use like the power sources on Earth, or is it too dangerous to use on Earth?
No, they are used on Earth. They are used for terrestrial missions. The Department of Defense uses those, and we do assemble and test and deliver for national security missions. I'm not privy to what those missions are. I do know that in the Arctic, they've been used for communications, to power communication devices in that area. But I just don't know what the military uses those for on Earth. It's kind of hard to fuel and test them and deliver them to some, remote location, and then you don't know what happens. And then sometimes we get them back. We go pick them up and we defuel them.
So Kelly, I'm so curious what your take was on the sequence in the movie The Martian, where the astronaut digs up the RTG, I think from curiosity, and
Right.
actually uses it as like a heater in his rover.
Yeah. So we tried to invite Matt Damon out for this last build, but he never answered.
Bummer.
I mean, that's kind of rude, right? But anyway. So yeah, perfectly feasible. And as a matter of fact, when that movie came out, we got on board and tried to come up with answers to questions that we thought might be asked. But certainly it would be generating heat, as I think it was Steve that asked the question about how long these would work. So at the surface of the cylinder, the temperature at the beginning of the mission is going to be about 320 degrees Fahrenheit. So, as of course the radioactive material decays, it's going to generate less heat, but absolutely, certainly he could use it for heat. Now, what he doesn't want to do is use it for heat for a long period of time. Because when you're dealing with radioactive material, time, distance, and shielding are your friends. So you want to spend the least amount of time you can in the radiation field, or you want to distance yourself from it, because certainly the effects of radiation sickness are not worth the heat.
And that's what I was so curious about. How quickly would he get radiation poisoning from being that close to that cylinder?
So it turns out that these particular units, you can get pretty close to them for quite a long period of time. I mean, we don't pick up a lot of dose at the level that it's fueled. So really you could stay around it for, I would say months. Before you would probably see ill effects. Yeah, so we have people. I mean, you saw a bunch of us standing around it taking a picture. I have picked up 0 dose of radiation standing that close to it. I mean, and it wasn't for a long period of time, but we are actually doing some radiation studies to use a rover on the moon and on Mars, similar to what you're seeing here, to transport people around the colony. So we're doing some dose estimations there, and suggesting what kind of shielding one might put between the RTG and the astronaut driving the rover. So that's kind of fun.
Deborah, do you have a question or comment?
Well, I was reading simultaneously that 238 emits alpha particles primarily.
Yeah, so there's an alpha,
which can be shielded readily, but
correct.
Yeah.
Mm-hmm. So the neutron emission from them. So yeah, there's an alpha N reaction, alpha emitter primarily. Alpha particles can be stopped by, I think, paper.
Yeah.
Mm-hmm.
And that's essentially helium, isn't it? Is that where the helium gas comes from?
Well, the helium gas comes also from the decay of the radioactive material.
Mm-hmm.
So separate thing.
Okay. But there's other radiation emitted besides the alpha
Yes.
part?
So there is some beta and neutrons. So the neutrons would be the most energetic, and it's the neutrons that we really that we design our equipment to shield from. So hence the plastic shielding that you saw. That's protecting the worker from neutrons, and also the inner atmosphere and assembly chamber where we put the fuel stack in. All of the walls on that chamber are filled with water. So water is a great shielding for neutrons as well.
Oh, thank you.
Great question.
Well, you mentioned, if you were using nuclear energy to essentially ignite for thrust engines, what element would you use? What isotope, and would that be of danger to astronauts?
Okay, yes, and I'm not sure, and yes. So reactor fuel is a different beast than these clads here, and if you take a look at those slides, I can't remember if the fuel type is in there. I think it's a graphite type fuel, or perhaps it's a metal fuel, but I'm sorry, I don't know that much about reactor fuel.
Sure.
Sorry, but certainly radioactive, and yes, the reactor would be harmful. I mean, because it's emitting radiation to humans.
Yeah. Thank you.
Well, it's just past 8:30, so we should probably do the door prizes and raffle prize. And depending on your timing, Kelly, you're welcome to get back to the rest of your life, or if you want to hang out, there might be one or two more questions after we do the raffle prizes. But thank you again so much for the presentation and answering all of our questions. Really appreciate it.
The opportunity. I really enjoy doing these things, and again, I wish I could do it in person. I think I'm a little more lively in person. But
you were great.
Oh, thank you so much. You're very kind. But I enjoy it, and I hope I've encouraged you to go out and do a little investigation and maybe be on board with supporting us and our adventures using radioactive material. Thank you so much.
Yeah, thank you. All right, well, the good news is I have almost as many door prizes as people who are here, so the chances are good. So we're gonna start out with one of these awesome locally made stickers by Holly Sage Art, same folks who do the Wyoming Stargazing website. So excuse my dog in the background.
Good evening, Monty.
It's Monty. So the winner of that sticker is Dakota Moore. And the way all these prizes work is you can either pick them up at the Wyoming Stargazing office if you're local, or I can mail them to you. So another eclipse sticker here, commemorative sticker from the 2017 eclipse. Winner of that one is Liz Mosley.
Thank you.
Yeah. All right, so the next sticker is a classic NASA sticker that we got, compliments of Scott Altman, who came and gave a presentation for us a couple of years ago. Winner of that sticker is Rita Edwards. All right, and I've got one more sticker. So this sticker is a sticker of the International Space Station, who we got from another astronaut who came and gave a presentation, Reed Weissman. And these are really cool stickers. The winner of that sticker will be Anne-Marie Wells. Okay, next door prize is this commemorative eclipse coin. So we made these for the 2017 eclipse. They're actually functional eclipse coins because they've got a hole in the middle of them, so you can actually project the partial part of the eclipse through the hole onto the ground. So you can watch that without looking directly at the sun. And they just have a beautiful picture of the Tetons on the background there, which I think you can see a little bit there. So the winner of the eclipse coin is Jeff Pinkham. All right, we've got two more door prizes. The first is a Wyoming Stargazing t-shirt. That's the front of the t-shirt. And here's the back of the t-shirt. Winner of the t-shirt is Linda Wasserman. All right, and the last door prize is the grand prize for the door prize. One of these incredible astrophotography prints made by our very own Mike Adler. And that was of the Helix Nebula, I believe, one of the planetary nebulas in our galaxy. The winner of that print is Deborah Brand.
Whoa,
Nice work,
wonderful.
Deborah. Okay, and now for the raffle drawing. We're going to raffle off another one of Mike Adler's eclipse print, or not eclipse, but astrophotography prints. Sorry about that reflection of the light there. And this is a stellar nursery, or an emission nebula, the birthplace of stars. Can't remember exactly which one that is, but we can look that up for you. And the winner of that print is this is funny, Steve Singer.
Is that your father?
It's my dad. The joke is that he won like 3 of these during the first year of the the speaker series randomly.
And I didn't even register for this meeting tonight. So please save that for a gift for somebody in a future presentation.
Well, this is a raffle ticket that you bought, Dado.
All right. In any case, still save it for a future presentation.
We'll pull another one for tonight. See if we can get a winner here. Thank you. I appreciate you passing up that print. All right. So the real winner of the astrophotography print is J.R. Dolby. J.R. is one of our volunteers and stargazing leaders who bought a whole bunch of raffle tickets last time. So that's what you get.
That's nice.
Thanks again, everybody, for being here tonight. Really appreciate it. Hope you enjoyed the presentation. And as I mentioned before, check back on the website soon, and we'll have all the next Speaker Series events posted up there.
Terrific. Thank you, Sam.
Terrific.
Thanks, Deborah. Thanks, Dad. See you guys later. Have a great night.
I need to know where to pick up.
Oh, yeah. Yeah, I can have it at the Wyoming Stargazing office for you, if that works.
Sure, where is that?
I'll send you the address and directions in an email.
Yeah, perfect.
All right,
I'm
sounds
thrilled.
good.
I'm thrilled. Thank
Yeah,
you.
it's a beauty.
Yeah,
Talk
it
to you
is.
soon.
I'm sure. Yes, thanks.
Yeah, you're
Bye.
welcome. Bye.
Oh, there you are.